Say you have two versions of a prompt and you need to know which one is actually better, not just which one felt better on one try. You've probably also noticed something stranger. Run the exact same prompt on the exact same input twice, and you can get two different answers. Those are really the same problem. It's called variance, the natural run-to-run variation in what a model outputs. In this lesson, we'll fix both sides of it. First, how to A-B compare two prompts properly so the winner you pick is real and not just a lucky roll. Second, how to reduce variance itself, so a single prompt behaves consistently once it's out in the wild, handling real inputs. Here's the trap. You run prompt A once, run prompt B once. B's answer looks a little better, so you pick B. You've actually learned almost nothing because models are non-deterministic. B might have just gotten a luckier roll on that one input. A single comparison is a noisy signal, not a verdict. To compare fairly, you need to test across many cases, and ideally average over multiple runs per case, not just eyeball one output against another. This is exactly why the eval set from earlier in this course exists. A/B testing two prompts is simply running both of them against that same frozen set of test cases and comparing how they score in aggregate. The FAIR procedure has 5 steps. Take both prompt versions, A and B. Run each one against the exact same frozen eval set. Score every single output with the exact same rubric or checks. Compare the aggregate scores, average score or pass rate. And where it really matters, add a pairwise judge comparison. For each case, ask which output is better and run both orderings to control for position bias. These two views answer different questions. Aggregate scores tell you how good each prompt is overall. Pairwise win rate tells you how often B actually beats A head-to-head, which is often the number that decides things. Here's a ready-to-use judge prompt that does exactly that, including the position bias check. Say A scores 80% and B scores 82% on a 15-case set. Is B actually better? Maybe not, and here's how to check. First, weigh the margin against the set size. A 2-point win on 15 cases is weak. A 10-point win is a lot more believable, and bigger gaps on bigger sets earn more trust. Second, check consistency across runs. Run the comparison again, and if B keeps winning by a similar margin, that's stable. If the winner flips, you're looking at noise and the two prompts are effectively tied. Third, look at where the wins come from. If B only wins on 1 or 2 specific cases, that might just be luck on those inputs. A win spread broadly across the set is the real thing. Sometimes the issue isn't which prompt wins, it's that one prompt is inconsistent, great one run, mediocre the next. A few techniques tighten that up. Lower the temperature, the setting that controls randomness. For extraction, classification, or anything a machine consumes downstream, run it low. Be more specific. Ambiguity is what lets the model make a different choice each run, so nail down the format, vocabulary, and rules. Constrain the output shape with fixed fields or a nums instead of free-form prose. Add a few examples to anchor style and format. And for reasoning tasks with one correct answer, use self-consistency. Run the prompt a few times and take the majority answer, saved for high-stakes cases since it costs extra calls. Here's a prompt that diagnoses variance in your own prompt and rewrites it to be more deterministic. Reducing variance isn't always the right goal. There's a real trade-off here. For structured, correctness-driven tasks like extraction, classification, or data transformation, you want low variance. Same input, same output, every time, so push temperature down and constrain hard. But for generative, exploratory tasks like brainstorming or drafting, some variance is actually a feature because you want different angles across runs, and a higher temperature helps you get them. The skill is knowing which mode you're in and tuning for it. Don't crank determinism on a brainstorming prompt and then wonder why every run gives you the same 3 boring ideas. And don't run a data extraction prompt hot and then wonder why the JSON keeps changing shape on you. Here's what to take away. A single output is a noisy signal. Always compare prompts across the same frozen eval set, scored the same way. Use aggregate scores for overall quality and a position-controlled pairwise win rate for head-to-head decisions. A small flickering gap is probably noise. A large, repeatable, broadly spread gap is probably real. Reduce variance with lower temperature, more specificity, constrained output shape, and examples, and reach for self-consistency on high-stakes reasoning tasks. And match the setting to the task: low variance for structured correctness, higher variance for creative exploration. You can try both prompts from this lesson right now, either in the interactive playground on this lesson page at Free Academy AI, or by pasting them straight into ChatGPT or Claude.